Okay, mic is on, so let's start talking about spring force. Okay, so linear springs, let's consider it a spring, a linear spring. Let's make that spring linear. Spring of stiffness K of stretch length L0, and one end of the spring is fixed, and the other end of the spring is attached to a block of mass M. What does it mean for a spring to be linear? Yes. Constant stiffness coefficient, but really physically, what does it mean? If you want to explain to a layman's term without introducing the coefficient, the stiffness coefficient, what a linear spring means. Maybe you can think of a linear function. What makes a function linear? Yeah, it's a straight line. Yes.
So there's no
No, not quite, not quite.
Only affected by length.
Yeah. So if I have a function that's linear, yeah, go on. What is it? I didn't hear it. Can you say again? Yeah, not quite. The spring can move in any direction. Here we're considering 1D motions, but in a bit we're going to consider kind of 3D motions of a spring. Well, let me ask you this. If I have a spring, suspended spring, and I have a mass of 1 kilogram suspended by that spring, and the spring has a certain deformation epsilon, what's going to happen if instead of having a 1 kilogram mass attached to the spring, I have a 2 kilogram mass attached to the spring? What's the deformation of the spring going to be? It's going to double. It's going to be 2 epsilon. So that's basically what a linear spring means. The deformation is proportional to the force acting on it. So a linear spring just means that the deformation is proportional to the force. Raise your hand if you've taken mechanics of materials, the mechanics class. Yeah. So in this class, did you learn about Hooke's law, linear materials? You studied materials in the elastic region, the linear region. So if you apply a force, they're going to deform. Once you remove the force, they're going to go back to their undeformed case, and the deformation is going to be proportional to the force. That's Hooke's law. That's Hooke's law. We're in the elastic regime. Now there could be nonlinear springs that are not proportional to the deformation. And then also we could extend the spring too much in some cases that it will plastically deform and it will not go back to its initial configuration. So that would be a spring, then we're not working in a linear regime anymore. Does that make sense? So we have linear springs. We're going to study linear springs. The force is going to be proportional to the displacement or to the deformation. Deformation proportional to force. Great. Okay. Where's my colored chalk? Here. So we have our spring. Here is the undeformed length of the spring. So when no force is applied to the spring, we have its length L0, the unstretched length. I'm going to call epsilon to be the deformation of the spring. So that epsilon quantity is going to be useful because we know the force is proportional to the to the deformation. So we need to quantify the deformation. We're going to call it epsilon. So L0 again is the unstretched length of the spring. And L is the current length of the spring. So at this state T1 is epsilon. Epsilon is this distance, L minus L0, right? Is it positive or negative? Positive. Raise your hand if you agree. The stretch is positive here. So epsilon we can call it deformation, or we can also call it a stretch. Okay. What about in the second case? This is my L, and then this is my epsilon. Is epsilon positive or negative? Do we agree? Okay. Now in both cases, I want to draw the free body diagram of my mass. What are the forces acting on my block of mass M? Normal force and weight force, right? So the normal, the weight, in both cases. And then I have the friction force, right? The spring force, I have the spring force, right? In which direction will the spring force be in case T1? Raise your hand if you agree with this. Great. What about T2? It's going to be in the opposite way. So what's going to happen is always the spring is going to try to push the mass so that the spring goes back to its unstretched configuration. So the spring force pushes or tries to push the block such that the spring goes back to its unstretched configuration. So if the block is being pulled this way, the spring is going to go back to its unstretched configuration in case T1. And if the block is pushed that way, the spring tends to go back to its unstretched configuration in case T2. And let me take a unit vector Ex along the direction of motion of the spring, Ex, and I can also take Ey. So in case 1, the spring force is proportional. The constant of proportionality is K, this stiffness coefficient of the spring. It's proportional to epsilon, and the spring force points along minus Ex. And here epsilon is positive. So that's the spring force in T1. Do we agree with that? So this is how I constructed it again. The spring force is proportional to the displacement, or proportional to the stretch. The stretch is positive, so this quantity is positive. The stiffness coefficient is always positive. So the stretch is positive in this case, and then the force points along minus Ex. What would be the prescription of the spring force in case T2? Take a minute, think about it. What would be the prescription of the spring force in case T2? Is it the same? Is there a sign difference? Think about it. Take a few seconds. Ideas, what is it going to be? The spring force in case T2, the prescription of the spring force. Yes. Yes.
Epsilon itself is negative, so you would consider epsilon like as its numerical form,
Well, let me ask this. Is it going to be K epsilon Ex, or is it going to be minus K epsilon Ex? Raise your hand for option 1. Who says it's option 1? Who says it's option 2? Okay, we have a disagreement. Discuss. Try to convince your neighbors. Okay, so let's take a vote again. Who says it's option 1? What about option 2? We have a majority for option 2, and I think the majority wins. You have to be careful. Right here, in this case, epsilon is negative. So in this guy, for this prescription, the force would point along negative Ex, but we know that the force points along positive Ex. So that's not quite right. Here, minus epsilon is positive because epsilon is negative. So then the force points along Ex, which is what we have. So in both cases, does that make sense? In both cases, the prescription of the friction force Fs is equal to minus K epsilon Ex. And this works both when the spring is compressed and when the spring is extended. Prescription of Does that make sense? Now that's the prescription for the spring force where the spring is just moving in 1D, in one dimension. And you've probably seen this expression before. You might have used S instead of epsilon or X. The X needs to be the stretch, the deformation of the spring. Now let's figure out the expression of the spring force for a general spring moving in any dimensions. So consider a spring in 3D. So consider the same setup but in 3 dimensions. So again, a spring of stiffness K of odd stretch length L0 with one end fixed and the other end attached to a mass, but that mass can now move in 3 dimensions. The same setup, but with the mass. Okay, so this is my general mass M moving in 3 dimensions. The fixed end of the spring is at A. So that's the fixed end of the spring. Okay, and I can write the position vector to point A, or A. The position vector to the mass M as R. Okay, and the spring has stiffness K on stretch length L0. How can I write L, the current length of the spring? Because remember, I want to prescribe the spring force, which is going to be proportional to epsilon, which is L minus L0. And then we're going to need to figure out its direction still. But for now, it's proportional to epsilon, which is L minus L0. L0 is given, say, in this problem. I need to find L. How can I express L, the current length of the spring? Yes?
The magnitude of the vector R minus L.
Raise your hand if you agree with this. Okay, great. That's it. Yes, that's the length L. Perfecto. So that's L. So now once we have L, we can calculate the stretch of the spring. Now, what is the direction of the spring force? Yes. Along ER, well, not quite, because here, if the origin is here, then ER is in this direction. The one thing we know about the spring force is that it's always directed, yes? Exactly. So what your friend is saying is that the spring force is always directed along the spring. So it's either this or that, depending on whether the spring is being stretched or compressed, but either way, it's along the spring. And a unit vector along the spring is R minus RA over R minus RA. Okay, so this vector, let me call it U and let me draw it. This vector points from RA to R. So that's my vector U. So the spring force is going to act along plus or minus U. Which one is it going to be? Let me ask this. If epsilon is positive, meaning that the spring is stretched, should this be a plus or a minus? Will the spring force act along plus U or minus U? Yes, minus. So if the spring is extended, the spring force is going to try to bring back the mass to the unstretched configuration of the spring. So the force is going to be along minus U. What about if the spring is compressed? Is it going to be along U or minus U, the spring force? So again, if the spring is compressed, is the spring force going to be along U or minus U? Raise your hand for U. Yes, that's it. It's U. So it's going to be along U. And to make it along U, epsilon is going to be negative in that case. So we're going to have to need to add a minus sign. So in both cases, the expression has a minus sign. And that's it. That's our general expression for the spring force for this 3D problem. The minus sign works either way, if the spring is compressed or the spring is extended. So in general, that's the expression of the spring force. It's actually very systematic. A lot of students get confused for the case of being stretched or compressed. Either way, it's the same expression. You can apply it in a very systematic manner. Does that make sense? Any questions? Questions? Okay, that's great. Let's do a couple examples of deriving the equations of motion for our simple harmonic oscillator when it's in horizontal, along the horizontal and along the vertical. So the same problem, the simple harmonic oscillator. I need to get its equations of motion. Okay, and I'm going to consider two cases. First, I'm going to take the origin . I'm going to take the origin here. Okay, so I want to find the equations of motion of this simple harmonic oscillator. The trick is I'm going to take my origin to be at the fixed end of the spring, which is not usually what I think you did before. So let's try to figure this out. I want to find the equations of motion. I'm going to follow the 4 steps. What's the first step? Step 2, that's step 2. Step 1, exactly, set up the basis and the kinematics. So this is my basis, and then I can write the position vector as x ex, and that's it. It's rectilinear motion, right? The velocity, I can write it as x dot ex. The acceleration, I can write it as x double dot ex. So that's my step 1. Step 2, the free body diagram. So how many forces do we have acting on this block? 3, right? 3. The normal force, the weight force, and the spring force. It really doesn't matter usually to me how you draw the spring force this way or the other way. As long as you write the expression correctly, that's fine. So the weight is equal to minus mg ey. The normal force is equal to ney. The spring force, I'll use the 1D equation here, minus k epsilon ex. Now, how can I write epsilon in terms of x? What is epsilon equal to? Exactly, L minus L naught. L naught is the unstretched length of the spring. Say it's given. What about L? Can I write L in terms of x, the current length of the spring in terms of x? This coordinate x here. Yes, how? I mean, that's gonna be simple, right? This is my position vector to the mass m. Its length is x, right? Which is the same as the length of the spring, right? Does that make sense? Okay, so that's just x minus L0. What is my third step? Yes? Balance law, the balance of linear momentum. F equals ma. And then I'm just going to add the forces. Minus mg ey plus n ey minus k x minus L0 ex. How many equations of motion am I going to get in this problem? How many degrees of freedom does this system have? How many coordinates, independent coordinates, do I need to express the location of the mass m? Is it 1 or is it 2? But be careful, m is moving on a straight line. It's rectilinear motion. Do I really need 2 coordinates to describe its motion? It's 1 coordinate. So how many differential equations am I going to get? 1. In which coordinate? X, ex, right? X dot, x and x dot. X is a function of time. And once I've solved for x as a function of time, I basically solve for the motion of the block. And then because I have this constraint that it needs to move on a straight line, I have the constraint force. That is the normal force, right? So how do I get the equation of motion? The equation of motion is going to be for x. It's going to be differential equation in x. So how do I get that? Yeah, I'll project along which direction? Ex. And I'll get minus k x minus L0 is equal to m x double dot. Mx double dot plus kx is equal to KL0. That's my equation of motion. Have you seen this before? Have you seen it maybe with this side being 0? Raise your hand if you did. If you have. Yeah. What's the solution to this equation? Say this side is 0. X double dot plus omega n squared x is equal to 0. It's harmonics, it's sines and cosines. Now, any questions? What do you think would happen if instead of taking my origin to be at the fixed end of the spring, what if I take my origin at the free end of the spring? What if we take our origin to be at the free end of the spring when the spring is unstretched? So I have the spring unstretched, and that's the spring stretched, and I'll take my origin to be at this location. Okay, and that's my position vector to the particle. So R is xex. That's step 1. Step 2. The free body diagram, that's going to be the same. But now if I want to find an expression for epsilon in terms of x, what is it going to be?
Epsilon will just be x.
So your friend is saying that epsilon is just going to be x. Do you agree? Yeah, does that make sense? Epsilon is just x. So the stretch of the spring, the displacement of the spring, that's just x. And x can be positive or negative. Positive if the spring is extended, negative if the spring is compressed, just like the stretch. So now I can, when I write the equations of motion, balance of linear momentum, F equals ma, I'll get minus mg ey plus n ey minus kx ex is equal to mx double dot ex. And projecting along the ex, sorry, I'll get minus kx is equal to mx double dot. So I solved the same exact problem, but I chose a different origin. I got a slightly simpler equation of motion. So in the upper board, x describes the position of the particle from the origin that is at the fixed end of the spring. And the lower board, x describes just the stretch of the spring, the displacement or the position of the mass from the free end of the spring when it's unstretched. So sometimes we can choose coordinates or the origin to simplify our equations of motion. This becomes suspended vertically. So let's do that. But before we do we have any questions? Questions? So let's look at the spring or the harmonic oscillator suspended vertically, or vertical harmonic oscillator. Okay, so we have a spring, stiffness K, and search length L0. What I'm gonna do is gonna suspend a block of mass M from the spring. And then the spring is gonna start to oscillate. So here, this here is the static equilibrium. So here, that's just the spring is being the mass M is being suspended by the spring, and the mass is not moving. So in both cases, in all cases, I have this being L0. And in this problem, I'm going to take my origin to be here. So that's my position vector to the spring. I'm going to take Ex pointing down. Okay, do you understand what's going on? So in the middle state, this mass is being suspended, but it's not oscillating. So this is an equilibrium configuration. The deflection here of the spring at equilibrium, we call it delta ST. Okay, this is also known as the static deflection of the spring. Okay, and again here I want to solve for the equations of motion of the spring, of the mass. What do I do? Yes. I'm going to put my basis. I took Ex, I took my origin to be located here, and then I need to write my position, velocity, and acceleration vectors. So R is just going to be X Ex, and this is my distance X from my origin, the length of R. V is X dot Ex, A is X double dot Ex. Okay, then what? What do I do? The free body diagram. How many forces are acting on the block?
2.
Yes, 2. The weight and the spring force. The weight is equal to minus mg Ey. What about the spring force? What is the spring force equal to?
Negative. It's a deflection.
minus k epsilon Ex. That's my expression of the spring force in 1D. If the spring is deflecting along Ex from over there. You can also, the 3D equations simplify to the 1D equation. Any questions? I took Ex to be pointing like that. Oh, I'm sorry. Yes. Ex. And let me double check when epsilon is positive, the spring is extended, like the case I drew here, the spring force points out minus Ex, which is 1. It's always nice to double check your expression, and it's always easiest to double check it when the spring is extended. Yes? Yes. Thank you. Anything else? Yes?
Does the epsilon encapsulate the static deflection?
Well, you tell me. What is epsilon here? In general, epsilon is L minus L0. And what's the current length of the spring? What is the current length of the current length of the spring is all this, right? So what is it equal to? L0 plus static deflection plus X. So that's my current length of the spring. Does that make sense? So L is L0 plus the static deflection plus X. So my stretch is the static deflection plus the deflection due to the oscillations above the static configuration. So it's easiest if we go back to our initial definitions. This epsilon is L minus L0. What is L, the current length of a spring? Let me draw it. What is it composed of? Very systematic. Step 3, I'm going to write the balance law, F equals ma. And I'll have mgEx minus k delta static plus X Ex is equal to m x double dot Ex. And I can project this along Ex to get minus mg minus k, the static deflection plus X is equal to m x double dot. Now what I want you to do is I want you to take 1 minute and solve for the static deflection. Figure out a way to solve for the static deflection. Before I let you do this, what is x double dot? 0. Right. So go ahead, solve for the static deflection. What is it gonna be? So you would just write F equals ma for this state, and a is just 0. Raise your hand if you've got an answer. Okay, one answer. I need more. A couple. I need more. Second, you're doing the balance law for the static configuration case. X is 0, x double dot is 0, x dot is 0. What is x in the static configuration case?
Oh. 0.
Yeah. Okay, so what is my delta static? X is 0, x double dot is 0.
Is it M here
Well, I have an answer, mg over k. Do your classmates agree? Do we agree? Yes?
So should there be a negative in front of the mg?
No, thanks. Okay. So mg over k. So basically the mg times k delta static term, they cancel out. And what am I left with? Mx double dot plus kx is equal to 0. The same equation that I got for the horizontal harmonic oscillator. Mx double dot plus kx is equal to 0. And that's the case because I took my origin to be at the static equilibrium configuration, at the free end of the static equilibrium configuration. That would have not been true if I took my origin to be here or here. I would have had, x differing by a constant. Does that make sense? Any questions? So if you end up taking a vibrations course, what they're going to do is they're always going to consider oscillations about the static equilibrium position. That gets rid of the weight term, balanced by the static equilibrium, the static deflection, I mean. Any questions? Okay, that's it for the spring force. I think we've solved between these two of the problems in the set. There's one more problem that you can solve on your own or in the exercise session tomorrow. And let's hop in and talk about friction. Friction, very interesting. Okay. Our quiz is going to be about friction, and today's quiz is individual. So make sure you pay attention and let me know if you have any questions. Friction force. Okay. So I want us all to do an experiment. Maybe grab any object, your phone, your iPad, a block-like object, or even any object, could be your water bottle, and put it on the desk in front of you. And let's do a simple experiment. Oh, you only do horizontal then. So what we're gonna do is we're gonna start and we're gonna put a small force and try to push the object. If the force is small enough, will the object move? No, right? But if I keep increasing the force, there's going to be a point where the object starts to move, right? So there is a critical value of the force. If P is less than P star, the object will not move. At a certain P star, at a certain force, the object will move. Usually the force required to sustain the motion of the object is less than the force required to initiate the motion. The force required to sustain the motion, okay, I'm going to call that P star double dot, is less than the force required to initiate the motion, which we already called P star. It's less than the force required to initiate the motion. That we already called P star. You can try an experiment. It's not moving. I want to get it to moving. I keep increasing the force. When it starts to move, the force needed to sustain the motion, constant speed is going to be less. Or sustain the motion at a constant speed. Or, yeah. Any questions? And what do you think is going to happen to the force required to initiate the motion if my object is heavier? Will I need more force or less force to initiate the motion? More force. And what about if the motion is going on? During motion, will I need more force or less force to sustain the motion if the motion is happening? More force. If the weight is more, I'm going to need more force to sustain the motion. So the forces needed to initiate and sustain the motion are going to be proportional to the normal force, to the normal force acting on the object. The forces, or P and P star, but I already defined what P and P star are. P and P star are proportional to the normal force So P and star are proportional to the normal force acting on the object. These observations enable us to develop a model for friction. A model for friction meaning some equations that help us describe how the friction force acts. Now this model is an approximation. It's due to Coulomb. Coulomb is a French scientist who was born in 1736 and died in 1806. So he lived 70 years. Okay. So this model for friction is due to Coulomb. There are other models for friction out there, but let me explain to you this model. And this model, we're going to see how it tried to capture these observations about friction. Okay. So the friction is of two types, static and kinetic. So we have static friction and we have kinetic friction. The static friction force is the force that's acting on the object while it's not moving relative to the surface underneath it. So that's the force acting on object if it's not moving with respect to the surface underneath it. Not moving whereas the kinetic friction force is the force acting on the object, the friction force acting on the object while it's sliding relative to the surface under it. Does the distinction make sense? So for example, if I have, this is an inclined surface I have here, and if I have my box of chalk, I put it on the block, and it's not sliding down. What kind of friction force is acting on this box of chalk? Is it static or is it kinetic? Static. But if I have my water bottle and I put it on the inclined surface and my water bottle slides down, what friction force do I have acting on the bottle? Kinetic, exactly. Okay, now the static friction force is an unknown. This force is an unknown force. We have to solve for it. How do we solve for it? We solve for it by relating the acceleration of the object to the acceleration of the surface under it. So since the friction force is static, the acceleration of the object is the same as the acceleration of the surface under it in the direction, well, it's in all directions. So the acceleration so the static friction force is unknown. We have to solve for it, knowing that, knowing that the acceleration of the object is equal to the acceleration of the underlying surface. Okay, so when I'm solving F equals ma, I have the friction and other forces is equal to ma. The acceleration of the object is known, it's equal to the acceleration of the surface under it. The friction force is unknown, we can solve for it. Now, the friction force is an unknown, but it needs to satisfy one condition. The friction force, the magnitude of the static friction force is less than mu s times n. This is called the static friction criterion. And mu s is the coefficient of static friction. And what this criterion does is that it tries to satisfy the other point. So when the friction force becomes big enough, or there's a certain cutoff beyond which the object is going to slide, that cutoff, we call it mu Sn, some coefficient proportional to the normal force. Okay? So there's a certain cutoff of the value of the friction force, the static friction force, beyond which the object is going to slide. Friction is no longer static. That cutoff is proportional to normal force. The constant of proportionality we call mu s, the coefficient of static friction. Does that make sense? A little bit? Okay? Now, kinetic friction is different. Kinetic friction is not unknown, it's known, it's prescribed. Kinetic it's a prescribed force. It's just a force that's proportional to the normal force. Again, using our observations from below, from above, the force needed to sustain the motion is also proportional to the normal force. So the friction force is proportional to the normal force, and its direction is opposite to the slip speed. Vrel, where Vrel is the relative velocity between the object and the surface under it. Okay? It is a common misconception that the friction force is just opposed to the velocity of the object. let me ask you this. What is the friction force between my hand and the chalk box? Is it static or is it kinetic? And what about now when I'm moving? Is that friction force static or kinetic? Why? Exactly, because we do not look at the absolute velocity of the object, we look at the velocity of the object relative to the surface under it. There are other situations where an object could be moving but the friction force is still static. For example, like a rider on a bus, an object on a conveyor belt. So these objects are moving but the friction is still static unless the object is sliding relative to the conveyor belt or the box is sliding in the back of the truck. Then the friction would be kinetic. Okay? Now, sometimes, let us do an example. Any questions about this? Okay, let's do an example. Say I have the same example, a box of mass m on a rough surface, coefficients of friction mu s, mu k. Let me write that given. Consider a box of mass m on a rough surface with static Okay, so the kinetic friction coefficient, some people they call it the dynamic friction coefficient, and instead of mu k they use mu d. So the kinetic or the dynamic friction coefficient. Consider a box of mass m on a rough surface, static and kinetic friction coefficients, mu s and mu k respectively, and the block is being pushed by a force P. The block is pushed by a force P. We need to find the equation of motion of the block. And P is horizontal. Okay. So a block on a rough surface, it's being pushed by a force P, a horizontal force P. We need to find the equation of motion of the block. And in this case, like in the example we did at the beginning of explaining friction, we do not know a priori if the block is sliding or sticking. Sticking meaning coefficient of friction is static versus sliding it's kinetic. So we do not know a priori or before solving the problem if the box is sticking or sliding. Any ideas what to do in this case? Take a few minutes, discuss with your neighbors. I do not know if the box is sliding or not. I need to find its equations of motion. What do I do? Any ideas?
Do we just solve for both cases?
Kind of. Ideas? Okay. That's what we're gonna do. We're gonna first assume that the friction is static and then solve for the friction force. And then what do we need to do to verify our assumption once we've solved for the friction force? So friction is indeed going to be static, in which case, which criterion needs to be satisfied? This, the static friction criterion. If it is indeed satisfied, then the friction is static and we find that's the problem. If it's not satisfied, then what do? Our assumption was wrong and friction is kinetic and we have to prescribe friction and solve it again. So again, we do not know if friction is static or kinetic. What we're going to do is we're going to assume that friction is static and we're going to solve the problem assuming that friction is static. And from this, we'll be able to solve for the friction force. Once we've solved for the friction force, we're going to see if it satisfies the static friction criterion. If it does, then we're done. Our assumption was correct. If it doesn't, then our assumption was wrong and friction is kinetic and we have to solve the problem again based on that. Okay? So let me write these steps and let us go through them. So steps, first we're going to assume friction is static. Okay? And then solve for the friction force. Okay? And we then check if a static friction criterion is satisfied. So if the friction force is less than mu Sn, if it's true, yes, then assumption was correct and we're done. Friction is static and we're done. If it's not true, then friction is kinetic. And we can prescribe the kinetic friction force, Ff is I minus mu k and V rel over V rel. Okay, and solve again. Any questions about the plan? Does that sound like an okay plan? So let's apply. Oops. Assume okay, and we're gonna still follow our 4 steps to solve for the friction force. So step 1, we're gonna set up our bases. Maybe I'll take my origin here. Ex, Ey, and I can write by position vector. The motion is just rectilinear, so x ex. V is x dot ex. A is x dot double dot ex. Okay. Step 2, I'm going to draw my free body diagram. How many forces are acting on my block? I have a 3, I have a 4. Raise your hand for 3. Raise your hand for 4. Well, think about it, discuss. Is it 3 or is it 4? Is it something else? What are the 4 forces? Weight, normal, friction, and the force P. So that's 4. Anything else? I don't think so. Weight, normal, friction force, and P. So here friction is static, so I do not actually know how it's pointing this way or the opposite way. It doesn't matter. I'll just say that it's some force along the x. Weight is minus mg Ey, and is Ney. The friction force, here I drew it to point along minus Ex. I could have drawn it to point along Ex, I just do not know, it's an unknown force. And the P is P along Ex. Okay, step 3, I'm going to write my balance law. F equals ma. But what is A in this case? 0, why? Yes, because I've assumed that friction is static and my surface is not moving, it's fixed surface. So the acceleration of the block is just 0. The block is fixed to the surface. Does that make sense? Okay. Minus mg Ey plus n Ey minus ff Ex plus Pex is equal to 0. How do I solve for the friction force? Yes? Project on Ex. And I'll get that the friction force is just equal to P. I can solve for the normal force by projecting along Ey. So far? Awesome. Okay. And what do I do next? What is it? The static friction force is equal to P.
Like the maximum static force.
Right. I need to check if I need to check if the friction force satisfies the static friction criterion. So the static friction criterion is if the friction force is less than mu Sn, then if P is less than or equal to. Okay, so this is my static friction criterion. If P is less than or equal to mu S mg, then the friction is static. Otherwise, what would happen? So I do not know the value of P, but if I were given the value of P, I would just calculate this. And if this is valid, then friction is static. If it's not, then friction is kinetic. What do? Is friction force an unknown, or is it now known? Now it's like we know it's kinetic. It's a known. It's known. It has a known expression. So the friction force would be equal to minus mu k, the normal force, times v rho over the magnitude of v rho. Okay? So if the block is moving, what is the normal force acting on it equal to? What is it? Is it still mg? Raise your hand if you think it's still mg. Okay, raise your hand if you think it's not. Maybe discuss, think about it. Is the normal force still equal to mg? Is it gonna be, raise your hand for yes, normal force equal to mg? Yeah, I think that's the, if F equals ma along Ex, you're still gonna get the normal force equal to mg. There are no other vertical forces and the motion is rectilinear. Now, there is a different problem you have in your homework where you have the force P being applied like this at an angle, making some angle with the horizontal. In this case, the normal force is gonna vary with P, but that's not the case here. Here, the normal force is still going to be equal to mg. What about v rel over v rel? In which direction is the block going to move? Along Ex, right? So that's just going to be Ex. So my friction force is going to be minus mu k mg Ex. The block with the force P is going to tend to move along Ex. The friction force is going to be, the kinetic friction force is going to be opposite. Okay. Now this becomes a little bit more tricky if you have, for example, a box on a truck and the truck is moving and the box is moving with respect to the truck. For this, you have to be very careful figuring out v rel as being the velocity of, say, the box minus the velocity of the truck or the point on the truck under the bus. Okay, you have to be very systematic. Okay. But for this, it's simpler. The friction force is minus mu k mg. I still want to find the equation of motion. What do? So I have my free body diagram. Force P, weight, normal, friction force. Now it's equal to this. I want to find the equation of motion of the block. What do? Yes? Yes, exactly, the balance law. So the balance of linear momentum. So it's kind of like here where step 1 is the same, step 2, a slightly different expression for the friction force. Step 3, the balance of linear momentum, F is equal to ma. Is A equal to 0 in this case? No, A is an unknown, the acceleration of the block, which we want to find. So we'll have the minus mu k mg Ex plus P Ex minus mg Ey plus n Ey is equal to mx double dot Ex. Okay, and I can project along Ex to get that minus mu k mg plus P is equal to mx double dot. And that's a differential equation of motion for the block. So once I know P as a function of time, I can solve for X as a function of time. So that's the EOM for this sliding block. Any questions? Okay then. For everyone who arrived late today, I just want to remind you of the post I put on ed. Please do keep checking the ed posts. 2 lecture videos that you need to watch. One of them about calculating the curvature of a plane curve. The other one about the Serif-Rennet formulas that you're gonna use in homework 3. So please do check those out. And I put an announcement about the midterm. It's next Thursday during class, covering everything till friction. We have a few previous midterms that I had that I gave in another university on the class website, and I think you can find a bunch of Berkeley previews online. What else? Oh, do watch the demos that are on the website. And I put a feedback form, anonymous feedback form, a link to an anonymous feedback form. Please fill that out. It would be great, to get your feedback to see if we need to change anything early on in the semester. Okay? Questions? Yes?
You may have said before, but is the midterm going to be more most closely related to like the quizzes?
It's gonna be so the quizzes is a little bit more difficult, right? Because you have more time, and here the quizzes you're just learning the concept, and we're asking you about basic ideas about the concept, whereas the exam you've solved all the problem set problems, which is very important. For example, in friction here we've solved just 1D problems, and the problem sets you have a particle moving on a plane, not just a rectilinear motion. So you need to solve those problems. You might get a problem like this in the final. We are posting the problem set solutions. You are solving more in the exercise sessions and the discussions, and there are some solution videos available online. You can always ask us questions in office hours or on it. Okay? Questions? Okay, let's go ahead and get started. This is going to be individual, so please put all your electronics away. And it's one easy problem and another bonus problem that's a little bit harder. Try to solve both. You have until 12. Please put all your electronics away. Yeah, all the notes are on the board. This one has to do with friction only.
Could I ask a question about that?
Yes.
Or I guess how do you determine that, or how did you determine that, like the static criteria is not working?
I did not. I don't have the value for piece. I said if it's working, then that's fine. If it's not, then you have. Otherwise, you have to do that.
Okay, but you usually have like numerical.
Yeah, you have to numerical values to do that. Everyone has a copy? Okay, great. Good luck.